All right, so what direction does static friction act here? Sorry, I got interrupted. If I'm pulling here, one might think that the entire thing is going to translate to the left. If it translates to the left, point P here would move into the left relative to the ground, which would suggest a frictional force going to the right, or acting to the right. If we think rotationally though, when I pull here about the center of mass, that would want to make this object rotate counterclockwise, which means that point P would want to slip to the right past the ground, right? Meaning static friction should act to the left. Ah, darn. So neither of my two analyses sort of cohere to the same set of rules, so I really don't know what direction it's going to act. So really here, I do have to just take a guess and then do an analysis that isn't based on what that guess is. And if you guessed what that analysis is, yep, it is put the pivot at point P again. And so I'm just going to put static friction acting this way. I don't know here, using my torque analysis, which would make it act that way. I'm just guessing because the lever arm distance is short there that the translational analysis is better. I don't know, I'm making stuff up as I'm going along here. All right, let's keep the same consistent declarations. To the right, up, and clockwise are positive, so I have linked declarations. I think the analysis here is pretty clear, because if I do this, if I do a sum of torque about point P is equal to I alpha, the only torque that's providing, force that's providing torque is 4 I alpha, and this would get the object to rotate like that around there, which is counterclockwise, so negative. Therefore, alpha is less than 0. It's going to, therefore, by using the condition of pure rolling, ACOM equals alpha R, ACOM is less than 0 as well. This thing is going to start to rotate to the left. Now, can we figure out then what the direction of static friction is? Well, if I just did sum of forces in the x direction is equal to max, F4 minus F, or actually minus F4 plus Fs is equal to max. Oh, I don't know. This is not conclusive because I don't know the relative value of these two, so I don't know which force is bigger, and therefore that doesn't provide a conclusive analysis. So let's shift the pivot back here to here to see if that provides a conclusive analysis. Once again, we're going to have that sum of forces, or the sum of torques, but this time about the center of mass, is equal to I com, this is IP, alpha. And here I'm getting a negative torque due to 4, and also a negative torque due to static friction is equal to I com alpha as well. And yeah, this is not going to provide a conclusive analysis because this is negative F4 little r minus Fs big R is equal to whatever I com is times whatever alpha is. Yeah, it looks like we're not really getting a very conclusive analysis because maybe we could simultaneously solve these. This would be negative F4, and then that lever arm distance from the bottom here would be big R plus little r. I not about the center of mass, but this would be about I com plus the mass of the thing, and the shifting distance would be little r plus big R squared alpha. And I guess, could we simultaneously solve these two in order to see if there is some sort of relationship between Fs and F4? I guess we could if we had to find out what the direction of Fs is. This problem doesn't require it. So this analysis doesn't seem to conclusively prove which one, but let's go down this route for a little bit just to see if I can figure out something about it. Probably the easiest thing to do here is either get rid of the ICOMs or get rid of the alphas. Let's get rid of the ICOMs. So ICOM equals negative F4R minus Fs capital R over alpha. Let's plug that in here, negative Fr capital R plus little r. ICOM is negative F4 little r minus Fs big R over alpha plus mr plus little r squared alpha. If I put an alpha over alpha here, then I can cancel out all the alphas. Let's see what I've got then. I've got negative F4 r plus little r is equal to negative F4 little r minus Fs big R plus alpha mass little r plus big R squared. I guess let's solve for Fs and see if I can figure out which of them is bigger. So I'm going to move Fs big R to this side is equal to F4 R plus little r minus F4 little r plus alpha mr plus little r squared. Oh, that's interesting there because that gets rid of that and this. So I've got Fs capital R is equal to F4R plus m alpha a r plus little r squared, divide through by big R. Fs is equal to F4 plus m this, and there you go. I think that that pretty well explains then that Fs has to be bigger than F4 in this case, right? Because it's F4 plus something. Oh, except, dun da da, remember, trick, alpha. What did we figure out about alpha? Alpha was less than 0. Oh, wow. That means, therefore, we can conclusively prove that F4 is indeed greater than Fs in magnitude. But we don't really, I mean, we know how much greater, but does that really tell us then, in terms of this equation, what's going on? Well, let's see if we can play with that now, because we had negative F4 and then plus, putting that in, we know that Fs is equal to F4 plus m alpha r plus, well, r plus little r squared is equal to max. And so what does that do? I think that that's just going to get us down to tautology, folks. It looks like we can prove which of those is bigger, but that doesn't really help us figure out what direction that Fs acts at the end of the day. It looks like we need to know a little bit more about the parameters of what r and little r and big R are in order to answer that question, but still interesting nonetheless. So let's go to the next one. We'll go to F1, right? By the way, that problem, it's very easy to go down the rabbit hole in that problem, and I have in the past with some classes. So we have F1, we've got, just for sake of consistency, here we go, Fg and Fn. Let's figure out what direction Fs acts. Well, first, if F1 acts to the right, you might think that the whole thing translates to the right, meaning the point of contact's moving to the right, Fs would act to the left. Okay, so now let's assume that it would rotate about its center of mass. If I pull like this object would rotate counterclockwise, and that means the point of contact would be moving to the right with respect to the ground. Oh, good. Both of our analyses, unlike the last one, end up with Fs acting to the left. So I think we could be fairly confident that that's true, but let's work it out from here. Once again, I don't want my analysis to be contingent on the direction of Fs, so let's put the pivot there. Sum of torques about the point P is equal to IP alpha, and there you go. Here, if that's my pivot, this object would rotate this way clockwise, so it's a plus torque due to 1 is equal to IP alpha, therefore alpha is greater than 0, therefore a com is also greater than 0. There you go. Sum of forces in the x direction is equal to max. F1 minus Fs is equal to max. So that also lets us know that Fs is probably going to be less than F1 in order to have Ax be a positive number. In terms of this, if we put the pivot there, F1 would cause a rotation which would be negative in that case, and Fs would cause a rotation that's positive once again, but this has a larger lever arm distance than that, so it's hard to actually do an analysis there, but I think we can be reasonably confident that both our translational rotational analysis came up with the same direction for Fs. So once again, if I need to prove, by the way, what direction Fs goes, our goal would be to find an expression for Fs and figure out if that expression was positive or negative. And if we find out an expression for Fs, whether it's positive or negative, that lets us know if we put it on our diagram in the correct or incorrect place. All right. And last, we have here F2. Okay, and F2 is such that the geometry says that it goes at an angle such that it would act through point P. Oh, this makes this pretty simple, folks, because if we put in what we've got going on here, FG and FN, if I pick this as my pivot, if you look, no matter what, and even when we draw in the Fs, this is going to be that the sum of torques is equal to 0. That object does not begin to rotate. So there must be some angle here, theta, such that F2 could act that would cause it to not roll at all when pulled. Well, that's pretty easy there. What direction does Fs act? I can just go straight to the math because I know that if the sum of torques is 0 and it's not going to move here, I need the sum of forces in the x direction is equal to 0, and therefore since this has an x component, that means Fs must act to the left in order to cancel out the x component of F2. So there you go. What direction will it rotate? It's an analysis based on shifting around pivot points, looking at my sum of force, sum of torques to prove whether Ax or alpha is positive or negative, and we can use that analysis in order to figure out what the direction of static friction is in most cases. And so there's a series of problems through this chapter where we're doing pulling on forces on objects, and oftentimes we don't know what the direction of static friction is, but luckily we have an analytical tool that gets us out of that bind, and then we can use other tools then in order to figure out what the direction of the static friction is. The last caution about these types of problems, if you're going to shift around your pivot, right, like this would be sigma tau p. If I'm going to shift that to sigma tau cum, remember that the i's in these cases would be different, and I have to use the parallel axis theorem when talking about IP in order to get some sort of reasonable conclusion.